Welcome back to part 3, the finale video in this short little series over a brief introduction into the calculator portion of the numerical approximator. And now I'm going to go over the final methods in matrix algebra. And to begin, I'm going to go over naive Gaussian elimination, which simply performs naive Gaussian elimination on the parameterized matrices. So it has two argument types. The first one is going to accept a matrix and a null value, where it assumes that the first matrix is an n by n plus 1, or it can accept two matrices where the first matrix is symmetric and the second matrix is an n by 1 matrix. So the purpose of naive Gaussian elimination is to take a system of linear equations and row reduce that into echelon form almost, to a form of row reduced echelon form, and then perform backward substitution to where you can actually solve for the solution of the matrix. So now we can say our mat is equal to our iris. We can simply get the first 5 rows. Or actually, it has to be symmetric. So let's get the first 3 rows and go from 0 to 3. So here we have our mat, which is an n by n plus 1. We can now perform naive Gauss on mat, pass in null. So here we have our equivalent matrix. And what we can do now is we can now we can now perform backward substitution. So back sub here. So you can pass it in. So back sub of mat, missing a comma, pass in null, failed backward substitution. Hold on. So if we go back here, we can actually extract these matrices from naive Gaussian elimination simply by saying temp is equal to naive Gaussian elimination, and we can now say temp is now we can get our B matrix. So our temp B is equal to our get call of temp on the third column. So we want to get this column right here. This is our row reduced B matrix, and now we can get our temp is equal to, actually just delete call of temp. So there we have temp. Now we can perform backward substitution, passing in temp and temp B. So there we have our solution. So if we say our mat times our back sub, matrices must have the same, that's why, okay. So unfortunately I'm not taking much precaution into the actual matrix dimensions, which is very important to do. So if I was to say our B is equal to mat get call of mat 3, and I was to delete call of mat at 3, now we can actually perform our backward substitution. So our sol is equal to our back sub of temp and temp B. So there's a solution. If we were to say temp, our mat times sol, we should get our B matrix as we see here. So unfortunately, hopefully you guys can bear with me on that. I had some brain farts. However, if we go down here to forward substitution simply does the same as backward substitution, except backward substitution requires an upper triangular matrix, whereas forward substitution requires a lower triangular matrix. So forward substitution is used in the LU function for solving for the solution of a matrix. And then now we can also go over the final functions. These 3 static functions is positive definite, is square, and is symmetric. Is square simply returns whether or not the matrix value is square or not. Matrix is square if the number of rows equals the number of columns. Is symmetric simply returns whether or not the matrix is symmetric or not. A symmetric matrix is one whose transpose equals the original matrix. So if I was to say, we can say mat here, transpose of mat is this. Since our transpose does not equal our matrix, as 3.5 does not equal 4.9, then our is symmetric of mat should fail, as we see here. And a symmetric matrix has to be square in nature. Is positive definite simply returns whether or not the matrix value is positive definite. That is, all its eigenvalues are positive, so we can say is positive definite of mat. So our matrix is not positive definite. We can find the eigenvalues of our matrix as follows. Get the values. Simply needs to be square. So that does not work. True needs to be square. I get a mat. Oh, symmetric. Okay, that's why I read this as square. Our matrix here needs to be symmetric. So for us to find the eigenvalues, we need to find a symmetric matrix. So that is why is positive definite has failed. So that finishes up the matrix algebra part of the calculator, and that basically summarizes everything to do with the calculator. So hopefully you guys have enjoyed this short tutorial over the numerical approximator, its powers and its capabilities, and the functions available in this software. So thank you for watching.